Thanks, the organizers, for inviting me. I hope I'm audible to everyone.
Yes.
Okay. Right. So this talk is about, it's really about my attempts to understand cyclic homology and why they work for certain classes of algebras which you're familiar with C-star algebras. It turns out that the reason they work is because you can study them through a different class of embedded subalgebras, which are in a certain sense smooth. So, and then that's what this talk is going to be about, to study these embeddings. Okay, so now what do I mean by smooth embedding? So we all know that commutative C-star algebras are the same as spaces. Now, it turns out that cyclic homology for really topologically compact spaces are usually degenerate, so they give you zero. And this turns out to be because of lack of smoothness on topological spaces. So, and by that I mean there aren't enough derivations on this commutative C-star algebra CFM. So therefore, what Kunz had proposed at some point of time in the early 90s was you want to study spaces with some further
Hello, Devarshi.
yes.
Yeah. Actually, can you speak a little bit louder? People are requesting.
I see. Is this better?
Yeah.
Okay. Right. So what you want to study are spaces with some further structure. So if you're talking about a space, you want to study a manifold. And it turns out that these turn out to have more derivations. And you can talk about the de Rham homology of a manifold. So we want to do this for, say, an arbitrary C-star algebra or a Banach algebra even, and talk about smoothness in that context. And what one can do as an upshot, if you have such a smooth embedding, is use such a smooth subalgebra to talk about things like topological K3 and cyclic homology. Now, I won't really talk so much about cyclic homology or topological K3 so much, and instead just focus on the properties such an embedding should have and how they can be built. Okay, so let's start with what Kunz and Blackadder had proposed at some point of time. What they have done is defined a notion of a smooth subalgebra. And this is smooth in the sense that it has the following properties. And the first one is really the most important one, which is closure under holomorphic functional calculus. In the case of C-star algebras, we know of continuous functional calculus, which I'll review for normal elements. And of course, such a smooth subalgebra should be complete in an appropriate sense. And of course, certain maps which arise in cyclic homology should be continuous. But the issue with their approach was the topology which implements all these properties was far from canonical and was rather complicated to describe. So instead, what Ralph Meyer proposed through his work on cyclic homology was passage to a different way or a different category of where you can deal with functional analytic structures. And this is really the right domain where you can talk about such embeddings and functional calculus. And you of course have all your C-star algebras and Fréchet algebras sitting inside these categories in a nice way. And so this category is the category of bonological vector spaces. I suppose not many people are familiar with this world of bonology, so it would be worthwhile to talk about what I mean. And this really is it's really an axiomatic framework to do functional analysis. And what I mean by that will become clearer later, but just to tell you what is usually meant by an axiomatic framework, I'd like to draw analogies with topological vector spaces, where you have a set with some further structure, and the further structure, a subset of its power set, which you declare to be open and require it to have certain properties. And then you can talk about continuity in this more formal sense. Now, what bonology does is talks about a set with some further structure or some further collection of sets. And these collections of sets are what are called bounded sets. And this is a way to formalize what bounded maps are.
Devarshi, I'm sorry to interrupt, but I can't hear you at all. I mean, can you please speak closer to the microphone, perhaps?
Maybe I can try a different headset. Just give me a second. Is this better?
Yeah, this is better. Thank you.
Okay, perfect. Right. So as I was saying, we want to talk about a formal framework where we can describe bounded sets and bounded maps between bounded sets. And it turns out that if you want to do some kind of homological algebra category theory, as is the case if you want to talk about invariance of, say, C-star algebras or Banach algebras, then bonologies are a better framework than topologies. And if you know absolutely nothing, if you don't want to know anything about bonologies, then you can just think of us working with Banach spaces, but with all formal inductive limits added. So that's the category of inductive systems of Banach spaces. Okay, now a bit about the definition itself. So you start with a vector space, or you can even start with a set, but what's most relevant to us is a vector space. And you give it a collection, and this collection should satisfy the following. You want finite sets to be bounded. You want it to be hereditary under inclusion. So if you have a bounded set and something is contained in that, you want it to be bounded. And you want finite unions of bounded sets to be bounded. And you want the, let's say, the disk hull of a bounded set to be bounded. So in other words, if you have a bounded set and take the vector space generated by it, take the convex hull, then you want that to be bounded. Okay. So, and of course, so this is called a bonological vector space, a vector space with a bonology. And then you can talk about bounded linear maps between bonological vector spaces. And similarly, you can talk about bonological algebras, just like you can talk about topological algebras. But here are some examples. So, well, naively, you can talk about the finite dimensional subspaces of a vector space. This is the smallest bonology on a vector space. This is, however, not a very good bonology. It's too small. What you might be familiar with, although in a different terminology, which is the usual notion of boundedness, which is, let's say, you have a collection of elements, you want their norms to be less than some fixed positive constant. And this corresponds in terms of bonologies to the concept of a, well, the von Neumann bonology. So here you start with a locally convex topological vector space, so say a Banach space, and you declare a set to be von Neumann bounded if for each semi-norm you have boundedness in the usual sense. And this is really the same thing as usual boundedness, where by usual boundedness I mean a subset, say, in a Banach space is bounded if it can be absorbed by a ball of some radius around the origin. Okay, now a better behaved bonology is what is called a pre-compact bonology. So here you again start with a locally convex topological vector space, and a subset is pre-compact if for every neighborhood around the origin there's a finite subset such that this subset is contained in U plus F. So these are really the pre-compact subsets in the sense of topology, but this is also a bonology, and it's actually a very nice bonology to work with. And if I don't specify anything, whenever I refer to a topological vector space with a bonology, I implicitly mean it's a topological space, vector space with a pre-compact bonology. But it turns out that this is really equivalent to many other familiar notions, such as well, the topology of the topological vector space, but I'll come to that in a second. But so let's say if I talk about a C-star algebra, I really mean a C-star algebra with the pre-compact bonology. Okay, so now a comparison is what I was referring to with topological vector spaces. Of course, so as is the case with Banach spaces or C-star algebras, these are complete topological vector spaces. They're complete in a certain norm. So one can similarly talk about complete bonological vector spaces by taking just adding the limits of Cauchy sequences so that they're complete. Now, if the space is metrizable, as is the case with Banach spaces, then this notion of topological convergence is the same thing as the concept of a bonological convergence or Cauchiness of a sequence in the von Neumann and the pre-compact bonologies. So if you're dealing with metrizable spaces, then you're perfectly okay to work with topologies or bonologies just the same way. And of course, a consequence of that is if you're working with a metrizable space, then this topological notion of completeness is the same thing as von Neumann or pre-compact bonology completeness. Right, now you might then ask why introduce this framework at all? And the differences really arise when you talk about the categorical properties of say topological vector spaces or bonological vector spaces. And if you know something about this framework, then if you work with let's say complete bonological vector spaces over the complex numbers, and this with the projective tensor product is what is called a closed symmetric monoidal category. And closed really means that there is an adjoint to the, I think a right adjoint to the tensor product functor. And this is called the internal home functor. And it turns out there is a canonical bonology you can have for bounded maps between two bonological vector spaces. And this is something which is not the case with topological vector spaces, complete topological vector spaces, because there are lots of different kinds of topologies you can have for maps between two topological vector spaces. So this is a side categorical remark for why you should be working with bonologies and not topologies. But again, for practical purposes, for metrizable things, these are all the same things. Okay, so now the second part of my talk, which is about functional calculus. And this is, as I mentioned right at the start, we want to talk about a smooth subalgebra. And this smoothness should somehow be encapsulated by a holomorphic functional calculus. So if you have elements in a Banach algebra, you should be able to evaluate such elements for holomorphic analytic functions. And that's what's called holomorphic functional calculus. But before I get to holomorphic functional calculus, let me talk about, say, continuous functional calculus you might be familiar with from C-star algebras. And certain ingredients one uses to talk about C-star algebraic functional calculus. So the first thing is, so the idea is if you have a suitably nice function, say a polynomial, you should be able to talk about polynomials whose indeterminate is Banach algebra element. So that's polynomial functional calculus. Similarly, for rather important properties about invariance, if you know topological K-theory, and if in order to talk about homotopy invariance, you want to talk about exponentials in some Banach algebra. And you want to talk about logarithms as well. And these are usually given as power series in some variable. And you want to make sense of this power series where you can plug in a an element of a unital Banach algebra. So yeah, so that's the idea of functional calculus roughly. How do we get there? So we first recall what the definition of a spectral radius of an element in a unital Banach algebra is. And this is really the supremum of all lambdas, where lambda belongs to the spectrum of A. So this is just the usual spectrum of an element in a Banach algebra. And what's well known in functional analysis is that the spectrum of an element is non-empty and it's compact. And in order to really prove that it's compact, you show that it's closed and bounded. And the boundedness uses a certain spectral radius estimate. So you show that the spectral radius of an element is at most this limit, which involves the norm of the element. And furthermore, if you really want to talk about this f of A written right at the top, this is really given by a certain integral. It's called the Cauchy integral formula. Now, the key ingredient in that is to show that this resolvent map, which takes an element in the spectrum to A minus lambda inverse, or rather in the resolvent, you want to show that this map is analytic so that you can talk about this Cauchy integral formula. But I'll get to that. But so the key ingredient in this is to show that you can make sense of Neumann series. So that's just a geometric series. And you know that this geometric series converges if a certain norm estimate is satisfied. And if that is satisfied, then you can show that the resolvent map is analytic. And this is a key ingredient to prove, let's say, continuous functional calculus. So it's also continuous, of course. And the precise statement of continuous functional calculus is that for normal elements in a C-star algebra, you can define f of A for f inside continuous functions on this spectrum of this element. Okay, so now now you might ask, what about more general functional calculi? So what about holomorphic functional calculus? Now you need to weaken, of course, to a Banach algebra element. So that's what I mean by a general functional calculus. And what is more general is you want to define a class of algebras for which you can talk about holomorphic functional calculus. So I want to take a holomorphic function f and talk about f of A for f lying in holomorphic functions inside the spectrum of some Banach algebra element. And as you saw let's say when I was talking about how one can prove this, you need certain spectral radius estimates. So again, let me get back to this. So when you talk about the Neumann series of this A minus lambda inverse, what this really is a power series whose coefficients are negative powers of lambda, and this is a power series in A. So this is really what controls this power series, if that norm estimate is satisfied. And by norm estimate, I mean that the norm of lambda inverse times A to the some n, that is less than 1. So that's just the usual geometric series convergence condition. So the model is you need some kind of spectral radius estimates in order to talk about this resolvent map. And by talking about this map, I want to know that it's analytic. And yeah, so in order to really talk about more general algebras, we need to bring in a notion of spectral radius of a bounded set, which of course includes the spectral radius of an element. And yeah, so and now is where we really need a homological setup, and there's really no way of talking about these things with topologies. So, and that's the notion of spectral radius of a bounded set. So you start with a homological algebra, and you take a bounded subset, and you define the spectral radius of this set, of this bounded set, as the smallest r, such that you can control these bounded, such that you can control the powers of S and negative powers of R. So of course, if R is arbitrarily large, then this is always controlled, but you want to take the minimum such R. And this really coincides, if you talk about Banach algebra with the von Neumann bonology, or the usual operator norm and some operator algebra, then if you take S to be a singleton, so some element, then this is really the same notion as the spectral radius of an element. Because as I said, this is really what you want to control, the negative powers of R and S, and you want to take higher and higher powers of these. Right. And some, yeah, so this is what I was saying. Roughly, we want to control power series in several non-commuting variables. And in particular, if you have a Banach algebra, then you know that the spectral radius of S is bounded by the supremum of the norms of these elements, which is also what you have in the, well, let's say for a spectral radius of a single element, it's always at most the norm of the element. And in general, you know that the spectral radius of a bounded set is at least the supremum of the spectral radii of individual elements in a bounded set. But if you have a commutative Banach algebra, and it's very important that this commutative Banach algebra has the pre-compact bonology, then the spectral radius of such a of any bounded set is actually equal to the supremum of spectral radii of individual elements. Okay, so the conclusion is that we want to talk about spectral radii now, but of bounded subsets rather than elements of Banach algebras. And yeah, with a view to talk about functional calculus. Okay, so we're of course interested in algebras for which the spectral radius is finite. Now, because if you just stare at this formula long enough, you can, so if there is no such R, then we set it to infinity, because then we always know that we have bounded things. Right, so, but we're interested in things which have finite spectral radius. And such a class of algebras are called locally multiplicative algebras. But if you're not familiar with this bounded spectral radius and so on, then an algebra has finite spectral radius for every bounded set if and only if it is a strict inductive limit of semi-normed subalgebras. So here by strict, I mean that the structure maps of your inductive system are injective maps. But yeah, so as I mentioned right at the start, if you don't really care about bonologies, then one other way of looking at bonologies is through inductive limits. And in particular, if you have a complete bonological algebra, then such an algebra is locally multiplicative if and only if it is an inductive limit of Banach algebras. So what we're really interested in, therefore, are algebras which are inductive limits of Banach algebras. And these are called local Banach algebras because locally these look like Banach algebras. Okay. Right, so now let's first take an example of a local Banach algebra, and this is really a prototypical example. So if you start with a compact subset of the complex numbers, and you take a compact neighborhood, you denote by this h of k the holomorphic continuous functions with a holomorphic on the interior of k. So holomorphic functions. This is a closed subalgebra of continuous functions on a compact space, so therefore it's a Banach algebra. Now, if you choose a decreasing sequence of compact neighborhoods, Kn, then you can take their inductive limit so the Banach algebraic inductive limit, and what you get is just by construction a local Banach algebra. And this has a name. This is called, well, this algebra is called the germs of holomorphic functions on X. Okay, so, and it turns out that this specific, so the germs of holomorphic functions, these play a role in defining holomorphic functional calculus. Now, the setup, I repeat, is we start with a unital local Banach algebra. So we allow for inductive limits of Banach algebras, and an element whose functional calculus you want to define. And of course, just by the same proofs, you can show that the spectrum is non-empty. And the real statement of holomorphic functional calculus is that holomorphic functions on the spectrum to A well, is actually given by this f of A. This is an explicit formula for holomorphic functional calculus. So this is how you define f of A for some f lying in holomorphic functions on the spectrum of X. I think I mixed up A for X here, so this should be holomorphic functions on the spectrum of A rather than X. X is just the, well, yeah, X is this points on this curve gamma. But this is the formula, and this kind of makes sense of what I was saying. You want to be able to define this X minus A inverse, and this is where you need this spectral radii machinery to make sense of this resolvent map. And this map is unique such that the identity on the spectrum maps to X. And of course, some properties of this is that the spectrum of f of X in A is contained in f of the spectrum of X in A. And another property is that the spectral radius of f of X is the maximum of the spectrum of f of lambda, where lambda is inside the spectrum. And in particular, if you have the identity function f here, then the spectral radius is the usual definition of spectral radius of an element in a Banach algebra. Okay, so that's holomorphic functional calculus for a local Banach algebra. Okay, so now some properties of these locally multiplicative algebras. And this is again one of the upshots of this bondological approach. I don't know if Kuntz and Blackadder had proved something similar for what I showed in the first slide of their notion of a smooth subalgebra. In particular, I know that it's badly behaved under quotients. So again, Ralph Meyer proved these theorems in the context of locally multiplicative algebras. And these properties are as follows. So if you take the completion of a locally multiplicative algebra, if you take quotients, arbitrary direct sums, inductive limits, and certain kinds of bondological embeddings, then these remain locally multiplicative. And similarly, and this is useful when you do cyclic homology, because if you have an extension of locally multiplicative algebras, well, if you have an extension of complete bondological algebras, and if the middle guy is locally multiplicative, then this is equivalent to saying that the kernel and the co-kernel are locally multiplicative. So again, this property would be sort of more in perspective if you know cyclic homology. Okay, so now the main part of this talk, which you remember right at the start, the main point of this thing would be to define some notion of smooth embeddings sitting inside continuous objects like commutative C-star algebras. And so now I'm going to have to bring in some definitions. So The first notion is that of uniform density. So whatever embedding we define should be dense in some sense, and the right notion is uniform density. So what is that? So if you have a map, a bounded linear map between non-logical vector spaces, then such a map has uniformly dense range if for any bounded sets there is a sequence of maps going the other way, such that f of the sequence converges uniformly to x. So it is a rather strong form of density. Okay, so that's the notion of a uniformly dense range that we're going to use in describing embeddings. Now, the main definition of this talk, which is isoradial homomorphisms. Now, you start with a bounded algebra homomorphism with uniformly dense range. Then you call this homomorphism isoradial if it maps, well, if the spectral radius of any bounded subset inside A is the same thing as the spectral radius of its image under F inside D. So it's really it preserves radii, in other words. Yeah, and of course, if this map F is injective, then we call A an isoradial subalgebra of D. And this is really a notion of smooth embeddings inside some bounded logical algebra. Okay, so that's as far as the abstract stuff goes. Now let's talk about examples which fit inside this framework. So you want things which are smooth in your intuition, such as smooth functions on a manifold. You want these to isoradially embed inside continuous functions on a manifold. And this was really the motivating example of this entire approach. So if you have a bond-logical vector space and a smooth compact manifold, for simplicity's sake. So this is again some more structural results I have to bring in about bonologies, but hopefully they help in the understanding of what these objects are. So you can write any such vector space as an inductive limit of normed spaces, at least if it is separated, I think. Now we need to define bonologies on, say, smooth functions on a manifold and continuous functions on a manifold. So the relevant bonologies are as follows. You talk about uniformly bounded subsets inside continuous functions on a manifold, taking values in a bond-logical vector space. So say the complex numbers. So you call such a subset uniformly bounded if its image inside this bond-logical vector space is bounded in a uniform way. So for all x and m and for all f and s. So this is a class of bounded sets inside this continuous functions on a manifold. And similarly, you can talk about a subset inside continuous functions on a manifold as uniformly continuous if it is uniformly bounded in the sense above, and uniformly continuous as really a set of functions from M to this Banach space, so this topological vector space Vi. So there we can make sense of continuity. And yeah, so now you call a subset of this smooth functions on a manifold bounded if whenever you take compositions of vector fields from this manifold to M, then these are uniformly continuous as a set of functions for each bounded set. Okay, and so I did not show you the topological approach of Kuntz and Blackadder, where they also define some topology on, say, smooth functions on a manifold, but it is far harder to describe. And this is something which is, at least for my taste, easier to describe in terms of bonologies. Okay, and we equip continuous functions on a manifold and smooth functions on a manifold with these two homologies. So we equip continuous functions on a manifold with this uniformly continuous homology, and smooth functions on a manifold with this homology involving vector fields on the manifold. Okay, so now we can, and by the way, this was just to set up these algebras in the framework of homologies, and just to hopefully convince you that the homologies on these algebras are easier to describe. Right, and now viewed as homological algebras, you know that you can now conclude this theorem by as follows. So if you start with a local Banach algebra, so in particular just a Banach algebra, then smooth functions from a manifold into a Banach algebra isoradially embeds inside continuous functions on a manifold with values inside a Banach algebra. And of course, the proof of this really computes the spectral radii by hand. And the first thing you need is that you take some bounded subset inside continuous functions, and let's let this S of x denote the image of each element inside this bounded set for some point in the manifold. And you show that the spectral radius of this bounded set you started with is the supremum over the spectral radii of this S of x. And similarly, if you take a if you take a bounded set inside smooth functions on a manifold, you again compute a similar estimate involving spectral radii. Sorry. And you show that this map taking points in a manifold to the spectral radii of these S of x's, this is upper semi-continuous. And in particular, well, I'm talking about a compact manifold here. So this supremum actually becomes a maximum in both cases. So the spectral radii just agree. Okay, so that's just a word about the proof. You really check it by hand in this case. But yeah, the important thing is that smooth functions on a manifold embed isoradially inside continuous functions on a manifold, which is a bit of a sanity check. This is already known, of course. But this is probably the right framework to talk about more general kinds of isoradial embeddings, because we're not doing commutative C-star algebra theory here. Okay, so some more examples of isoradial homomorphisms. And this comes from inductive limits of C-star algebras. So if you have some inductive system of C-star algebras, and as I mentioned, these are always with this pre-compact homology. And if you take its inductive limit, then any uniformly dense embedding into some local Banach algebra is isoradial. Of course, in particular, each AI embeds isoradially inside its inductive limit. So let's take some examples of what this theorem could imply. So if you take matrices and inclusions into higher and higher dimensional matrices, this is a nice reduced inductive system of C-star algebras. And its inductive limit is n-infinity. So this embeds isoradially inside compact operators on L2 of the natural numbers. So that's an example of an isoradial embedding in this context of non-commutative C-star algebras. And then there are some other nice classes of examples from Ralph's thesis. And these are another class which comes from group actions. So for simplicity, let's talk about, let's say, a compact Lie group. And
Yes, I think this last example wasn't so clear to me. So this inductive limit result. I think your example is not an example of the theorem. In the example, you take the inductive limit logical algebra and embed that into a C-star algebra. In the theorem, you talk about the inductive limit C-star algebra embedded in something else, which looks a bit strange because the inductive system isn't used at all in your statement of the theorem.
I think the actual statement should be at the level of local Banach algebras embedding inside an inductive limit, and when that embeds inside some other local Banach algebra, and if the embedding is dense, then such an embedding is isoradial. I think I mixed things up here a bit with by invoking C-star algebras. But I think that each AI embeds isoradially into its inductive limit anyway.
So the correct theorem would say that you take the chronological inductive limit of the system AI and embed this into some other local Banach algebra.
Yeah.
And if you assume that each AI embeds isoradially into B, then A also embeds isoradially into B, which is maybe even an almost trivial statement because the bounded subsets of A are bounded in AI.
Yeah.
Okay, so the example is clearer than the theorem at least. So it's certainly a useful result.
Okay, thanks. Right, so now about isoradial subalgebras from group action. So let's start with, say, a compact Lie group and a Bonn-logical vector space that's complete. Now, a very important upshot, again, of this Bonn-logical approach is that it allows for defining smooth representations in a nice way. But before that, so we take any representation by bounded linear maps, and this induces a map from the group to the vector space. So this just takes G to pi Gx for x and v. And we call pi a continuous representation if this pi star is a bounded linear map. Again, this CGV is with this bonology that I spoke about earlier. And we call pi smooth if this pi star is bounded as a map, but into smooth functions on this group with values in a complete Bonn-logical vector space. Now, if you start with a continuous representation of a complete Bonn-logical vector space, then you can talk about its smooth elements, which are the set of all x such that this pi star of x lies inside this smooth functions on G with values in the representation V. So yeah, this is called the subspace of smooth elements of V. And to continue that, so this is the result that this subspace of smooth elements embeds isoradially inside. If you start with a local Banach algebra, and if you talk about smooth elements in that, then that embeds inside the Banach algebra. And of course, this can be done in greater generality, of course, with locally compact groups even. But I won't get into that. That involves some technical details. Okay. Right. So an example of this.
Is it dense always?
Sorry?
Is it dense always? This A infinity inside A?
Yes.
For any group action? Okay.
Yes. Right. Okay, so an example is, maybe the example would make this clear. So if you have the, let's say, this rotational C-star algebra with parameter theta, and this is the universal C-star algebra generated by two unitaries which satisfy this commutation relation, then you know that Schwartz functions inside this two torus. This embeds isoradially inside the rotation C-star algebra. So this is again an example of Schwartz function lying densely inside this rotation C-star algebra. And this is because this rotation C-star algebra has a canonical gauge action, given like this. And it turns out that this Schwartz algebra is actually the smoothing representation induced by this group action. So this is really this A infinity in this theory for this group action. Okay. So that's another source of examples of these isoradial subalgebras. And then some more examples if you have a finitely generated discrete group, so say the integers. And again, this is really a similar result in a similar spirit as the previous one. So you again want to embed smooth functions on this, which are defined as follows. So yeah, this is really the Schwartz space on G. And this embeds inside L1 of G, isoradially. So if you have just a discrete group Z, then you know that this Schwartz space on Z is just C infinity of the circle. And then this is well known in functional analysis, that the C infinity would just embed inside L1 of those. Okay, and then you can of course build isoradial homomorphisms once you have enough examples. So if you have an isoradial embedding, and if you have a nuclear Banach algebra, then you can tensor with that and again get something isoradial. And a particular example of this is if you start with some isoradial embedding, then the induced map on matrices over that algebra to matrices over the other algebra, that's an isoradial embedding. Similarly, if you have a smooth manifold, then
why is nuclearity is important? Why being nuclear? Is there any particular reason?
well, I'll have to get into the proof for that. I don't know off the top of my head, but I guess it comes in because you're tensoring, and that's it's when nuclearity usually enters a picture. I don't know if this is true for non-nuclear Banach algebras. Maybe Ralph would know a bit more about that. Is this true for non-nuclear algebras?
I don't remember, but if you took the result from my book, I probably found this proof and didn't find the proof in the more general case, and made the assumption because it was good enough for my purposes anyway. Yeah. So this result, even for matrices, is not completely trivial. There's some work involved because you don't really, well, you have to understand the bounded subsets in the matrix algebra in terms of things in A.
Yeah. Yeah, okay. So, yeah, similarly, if you have a smooth function, then smooth functions with compact support inside some local Banach algebra, this embeds isoradially inside smooth functions with that take values in A. And again, yeah, so none of these results are particularly trivial to prove, although they probably follow from these theorems, but they're not very easy to prove. Let me just second that. Okay, so now the question is, how do you build isoradial subalgebras? So if you start with a local Banach algebra, and if you have some dense subalgebra, so say you start with a Banach algebra and some dense subalgebra inside it, now, and you want to complete it with respect to functional calculus. And you also want to take the minimal such completed object, which contains A and is sitting inside B. And the way this is done, well, you can, of course, one way of doing this is formally you just take the intersection of all such objects. This would give you the smallest subalgebra of B, which contains A and is isoradial. But that's not very explicit. But explicitly, we can do the following. We can take bounded sets with spectral radius less than 1 and their disk hulls. So in other words, what you do is you take any bounded set and you take power series of this form. This no longer lies inside A. This is, however, inside B, but you just take the bonology or the subalgebra generated by such bounded sets, and its bonology is again given by these S infinities. So, I mean, and this is really what I've been saying from the start. You want to make sense of power series and several non-commuting variables. And by making sense, I mean you should be able to control the coefficients. So you just start with a bounded set and you take formal power series which satisfy these relations. And then you just take the topological algebra generated by these power series. And this is called the isoradial hull of A inside B. And this turns out to be the minimal such isoradial embedding inside B, which contains A. And an example of this, which would illustrate the point, is you can take B as the C-star algebra of functions on a circle. So this is related to the Laurent polynomials. And but in particular, if you take the completion of this, you get the Kunz algebra. And the hull of this guy inside the C-star algebra on the circle are actually holomorphic functions on the circle. Okay.
So Devarshi, there is a question by Ralph in the chat. Could you see?
I can't see the
Yeah,
chat
so
now.
he's asking, are the classes of algebras mentioned above topological algebras with extension?
Yeah. This wasn't a question to the speaker, but to Ajit Iqbal Singh, who has written down something in the chat above that, about various notions where the word logical appears, and I was wondering whether these so I suppose he says yes. So I suppose he mentioned some previous work of people studying functional calculus, spectral theory, holomorphic semigroups in certain topological algebras, and maybe things like homologies have been used in that setting already. But I guess that this might have been topological algebras, which also have some further properties which make them Born-logical. So here maybe the point is to work in a category where we don't even use any topology, just a Bornology. And that's good enough for certain purposes. And certainly there is a lot of work on spectral, functional calculus, spectral theory, and so on in certain topological algebras. And well, this is just a slightly different framework where certain things work very well. I think this was made for cyclic, so I kind of developed this theory in connection with cyclic homology theories. In fact, I followed work of Michael Puschnik, who also did similar things, but he used something like Fréchet algebras with some special ways of handling things. So he also worked with topological algebras, not really Bornologies, and I found that he made things more complicated by also putting on a topology in addition to the Bornology. So compared to these other works, one important message from this theory might be that the topology is actually not needed for us, we just need the Bornology. And getting rid of the topology might actually make things simpler.
Yeah.
Thanks a lot, Rob. Okay, Devarshi, you can continue.
Yeah. So, right. So here's the, let's say, the concluding remarks, which is how you apply all of this. So as I mentioned at the start, there are, well, the moral reason why cyclic homology fails for non-commutative or any kind of C-star algebra basically is that there are not enough derivations, which corresponds to the fact that there's not enough smoothness on C-star algebras. And that's why cyclic homology is degenerate, because it's built from, say, Hochschild homology, which is defined using derivations. Now, there is periodic cyclic homology, which works for certain choices of isoradial subalgebras. And again, so Kunz and Pushnik and so on, well, maybe not Pushnik, but I think the previous works prior to local cyclic homology they all use certain choices of embeddings, and then computed the periodic cyclic homology of that and got decent comparison results with topological K-theory. But the things which really work nicely for C-star algebras or more general homological algebras are analytic and local cyclic homology. And of course, something which I did not write down, but so these isoradial embeddings are also used to study topological K-theory itself, of course, and some fundamental properties of topological K-theory, such as homotopy invariance and Meyer-Vietoris. These use the spectral, homological spectral radius estimates. And yeah, and you have similar results also for topological K-theory, that if you have any embedding, basically any isoradial embedding inside your C-star algebra that you want to study, then the topological K-theory is the same, no matter what embedding you choose. And this is something which is probably not the case with periodic cyclic homology. And this is where you really need to bring in this notion of an isoradial embedding. Right. So, and yeah, that's the concluding remark, that HA and HL, so local cyclic homology, are invariant under passage to isoradial subalgebras. Okay, and now just the reason why I got interested in this is in relation to work with Cortinius, Kunz, and Meyer. So here we are really studying non-commutative algebras which arise in a non-Archimedean context. And what's most, well, and by that I mean non-commutative algebras over finite fields. And it's really most convenient to study these when we lift them to torsion-free objects, which are, well, let's say, algebras over the p-adic integers. Now, one might then ask is, if you have some lift R to the p-adic integers, so let's say this p-adic integer zp of t, so polynomials in one variable over zp, you can do several things with these. You can, well, it turns out that this lifted object itself is not ideal for cyclic homology purposes, but instead you can talk about its p-adic completion. Now it turns out that that is not a very good object either to talk about cyclic homology. So instead we want some intermediary object which contains this R, this lift R, and is sitting inside the p-adic completion. And it turns out that these objects, which are really, well, it's my speculation at this point that this can be formulated in these, in terms of this isoradial hull of R inside the p-adic completion, that these are the right objects. And the right objects are dagger completion. That's a different story. That's what we call them in our papers. So these dagger completions are the right objects from the viewpoint of cyclic homology and rigid geometry. And in particular, my speculation at this point of time is that this this last line that you see, that we also have an HA in our context, that this is invariant under passage to isoradial subalgebras. And this would be a nice result to have, and would relate it to some very old works from the 1960s. why certain kinds of completions are suited to this non-Archimedean framework. Yeah, so that's where I'd like to end.
Okay, thanks a lot, Devarshi, for this wonderful talk. So are there any questions or comments? You can just unmute yourself and ask. There are lots of comments by Professor Ajit Iqbal Singh. Yeah. So I don't see any questions. Maybe I ask a simple question. So is there a notion of K-theory for this generalized bornological algebras?
Yes. So that's a book by Ralph Kuntz and Rosenberg. So that develops topological K-theory for bornological algebras. And that has the right properties for, let's say, these local Banach algebras. So these are precisely the kinds of algebras which should be the domain of such a topological K-theory. And by that I mean you can prove homotopy invariants and long exact sequences.
Bot periodicity probably.
Yes.
Okay, thanks.
Maybe let me add that since there are inductive limits of Banach algebras, it's very easy to define K-theory for them and study its properties. In contrast, if you work with topological algebras, Frege algebras, for instance, there is a definition by Chris Phillips of K-theory for that, but it actually behaves somewhat different. It's more difficult, so there are some problems because one of the usual tricks is making things which are close to one invertible, and this doesn't work if you have unbounded elements. So like if you have a Frege algebra, you could have an element which has spectrum the whole complex numbers, and then invertibles are no longer open in your algebra, things like that. You can still define a reasonable topological K-theory, but the trick is rather that you reduce to Banach algebras using projective systems, which make things more difficult. But for local Banach algebras, things are just easy. It's just the same as for Banach algebras.
Okay, thanks a lot, Ralph.